Welcome to next lesson in WKB approximation. In the last class we have discussed the WKB wave function in classical region. Here we are going to discuss the WKB wave function in non-classical region. In the non-classical region, the total energy of the particle will be less than the potential energy. So the Schrodinger equation becomes d square psi by dx square plus 2m by h cross square into e minus v of x into psi x equal to 0. And the classical momentum p of x will be root of 2m into e minus v, and now this quantity will be purely imaginary because e is less than v. So we can take the modulus of this classical momentum. This is called modulus of p, which will be equal to root of 2m into v minus e. Remember, this is now v minus e and this term is real, and we take the positive square root, which is called the modulus of that classical momentum. The classical momentum is imaginary here. So the Schrodinger equation becomes d square psi by dx square minus 2m by h cross square into this e minus v becomes v minus e psi equal to 0. That implies d square psi by dx square minus this quantity 2m into v minus e psi is the square of this modulus. So it can be written as square of the modulus of p of x by h cross square psi is equal to 0. Here the solution is exponential. It is not oscillatory as in the case of classical region. So in order to compare with the classical region, this equation can be rewritten as d square psi by dx square plus I square into modulus of p whole square divided by h cross square psi is equal to 0. So this equation is similar to the classical region equation, except in that case p of x, now in the place of p of x here comes I into modulus of p of x. So proceeding in the same manner, we get the WKB approximate solution, that is WKB wave function in the non-classical region will be psi of x is equal to c by root of modulus of p of x into e raised to plus or minus 1 by h cross integral modulus of p of x into dx. Remember, in the classical region there was I by h cross, but here I and there will be another I here, that I into I becomes minus 1. So plus or minus into minus 1 is again plus or minus. It is actually minus or plus. We will keep it as plus or minus. It simply means that there are two terms, one plus term and one minus term. So this is the WKB approximation for the non-classical region. Remember, here it is p of x and there is no term. There is no I term. It is exponentially increasing or exponentially decreasing. There is no oscillatory behavior. An application of this non-classical wave function is tunneling. Tunneling means the tunneling of a particle through a barrier. For example, here in this picture there are three regions, region 1, 2 and 3. In region 1 and 3, the potential energy is equal to 0. And in region 2, there is a potential energy which is some function of x. And the total energy of the particle is E. That total energy is greater than the potential energy in region 1 and 3. So 1 and 3 are classically allowed region. And total energy is less than the potential energy in region 2. So region 2 between x equal to 0 to x equal to a is non-classical region. The particle cannot exist here by classical mechanics, but quantum mechanics says that there is a non-zero definite probability of the particle tunneling through this region into region 3. Now we consider a beam of particles which is incident from the right, that is which is coming towards the right in the region 1, and it will incident on the boundary at x equal to 0. Classical mechanics says that the particle should be returned to the same region because the energy of the particle is less than the potential energy. But quantum mechanics says that there is a small but definite probability of tunneling through the barrier. So here a part of the particle, a portion of the particle will be transmitted through the non-classical region and it will reach the third region. So that particle is called transmitted particles. Another part will be reflected back into the same region 1. So it is called reflected particles. So we consider the incident particle, say the wave function of the incident particle is a e raised to I kx, where k is equal to root of 2m e by h cross, because here potential energy in the region 1 potential energy is equal to 0. Therefore, now a part of this rays will be reflected back into the same region due to the potential barrier. Suppose that reflected particles are represented by the portion b e raised to minus I kx. So in region 1 there are two portions, an incident particle and reflected particle. The total wave function becomes a e raised to I kx plus b e raised to minus I kx. This is the exact wave function, not approximate, where a and b are incident and reflected amplitudes and k is equal to root of 2m e by h cross. Now in the tunneling region, that is in the region from 0 to a, that is called a non-classical region, we take the WKB wave function. The WKB wave function psi of x is equal to c by root of modulus of x into e raised to plus 1 by h cross integral 0 to x dash p of x dash dx dash plus d by root of p of x into e raised to minus 1 by h cross. Here there are two independent terms, one exponentially increasing term, another exponentially decreasing term, and their coefficients are in general different, 1c and 1d, where p of x is root of 2m into v minus e. Now if the barrier is very high means if v minus e is large or p of x is large, and very wide means we have to make the integral over a wide region. So the contribution of this integral will be very large. Then the probability of tunneling will be very small, because psi of x has to be, it must be finite. It is a basic condition on the wave function. In order to make psi of x finite, this exponentially increasing term becomes infinity if the potential barrier becomes infinitely wide. So that psi of x will be infinity. In order to keep psi of x finite, then the condition, the finite psi of x will be satisfied only if this coefficient c is equal to 0. So for a wide potential barrier and very high potential barrier, the constant c will be almost equal to 0 and there will be only the d part. In such case, the coefficient of exponentially increasing term must be small, and c will be 0 if the barrier is infinitely high or wide. Now the wave function in different regions looks like, in the region 1 it is a e raised to I kx, that is incident particle, plus b e raised to minus I kx, that is reflected particles. Then in the non-classical region or tunneling region, it is d by root of p of x and e raised to minus 1 by h cross integral 0 to x dash p of x dash dx dash. It is an exponentially decreasing wave function. And in the third region, psi of x, there will be f e raised to I kx. Here also it is e raised to I kx, similar to the first region, because first and third medium regions are same, and in the third region there are only transmitted particles and they are moving towards the right, and there will be no reflected particles in the third region. So there is no term e raised to minus I kx, where f is the amplitude of the reflected wave. So the picture of the wave functions in different regions are similar. This one, that is in the region 1 it is completely sinusoidal. In region 2 also it is completely sinusoidal but with a smaller amplitude. In region 1 the amplitude is a. And in region 2, the amplitude decreases from A to F as the wave function moves from x equal to 0 to x equal to small a. Now the transmission probability is the square of the amplitude of transmitted wave divided by square of the amplitude of incident wave. Now the relative amplitude of transmitted and incident waves are approximately, they are given by f by a, where f is approximately equal to the value of wave function at x equal to a, and a is approximately equal to the value of wave function at x equal to 0. So these two values can be obtained from the region 2. At x equal to 0 it will be d, and at x equal to a it will be almost e raised to minus 1 by h cross integral 0 to a p of x into dx. So the ratio is approximately equal to e raised to minus 1 by h cross integral 0 to a p of x dash dx dash. So the transmission probability is square of this one. It becomes minus 2 by h cross integral 0 to a p of x into dx. Because the prime can be eliminated here, our limit is now a. Therefore, the transition probability is e raised to minus 2 gamma, where gamma is equal to 1 by h cross 0 to a p of x dx. So the transmission probability decreases as p of x increases, or 0 to a, this width also increases. The transmission probability decreases as the height or width of the potential barrier decreases. So this is another one of the application of the WKB approximation for the non-classical region. It can be used for finding the transmission probability of tunneling through a potential barrier. Thank you for watching this video.